Hi good people, welcome back. In this video we're going to start our new chapter, chapter 19, testing hypotheses about proportions. We're going to go through this guided note-taking worksheet and answer two examples. And before you watch this video, I strongly encourage you to read the first 7 pages of this chapter. I put a link to this chapter in the Google Classroom post where you found this video. So if you haven't done so already, I would like you to pause the video, read those 7 pages, then come back. Alright, so there's a couple key terms that we're going to use in this video. The null hypothesis is denoted H sub 0, and it is the starting hypothesis. It is the starting hypothesis that there is no significant difference between specified populations. In other words, it is the hypothesis that nothing has changed. The alternative hypothesis is denoted by H sub A, and it is the hypothesis used in hypothesis testing that is contrary to the null hypothesis. The alternative hypothesis is not a single value, but contains all other values of the parameter that we consider plausible if we reject the null hypothesis. The p-value is the probability of obtaining a specified result under the assumption that the null hypothesis is true. When our p-value is less than 5%, that's usually enough evidence for us to reject the null hypothesis. What that means is that if under the null hypothesis there's less than a 5% chance of our sample proportion or whatever we're testing occurring, then we can conclude that the null hypothesis may actually be false. That level of 5% is sometimes called the significance level or the alpha of the experiment, and we'll get into that later in this chapter. Alright, let's take a look at our first example. Suppose Mr. Ritz has a coin that he believes is not fair. He believes that the coin lands on heads less than 50% of the time. The null hypothesis would be the hypothesis that the coin is fair. That is, H sub 0 is P is equal to 50%, where P represents the proportion of times that the coin lands on heads. What would be the alternative hypothesis then? Well, if I'm under the suspicion that the coin lands on heads less than 50% of the time, and the null hypothesis is that the coin does land on heads 50% of the time, our alternative hypothesis would be that the proportion of coins landing on heads is actually less than 50%. So to test that, I decide to flip the coin 50 times. To test whether the coin is fair, Mr. Ritz flips it 50 times, and it only lands on heads 16 times. So in our little experiment there, our sample proportion, 16 flips landed on heads out of 50 flips. That is 32%. Is that rare enough of an occurrence for us to assume that this may actually be an unfair coin? Well, to do that, we have to find the probability of obtaining this few heads when flipping the coin 50 times. We know that when flipping it 50 times, we would expect 25 times for it to land on heads. Of course, that's not going to happen every time, but is 16 small enough to warrant suspicion? Well, let's operate under the null hypothesis model. If this is in fact a fair coin, then the standard error of p hat of our sample proportion should be equal to P times Q divided by N. N was 50 flips. The standard error of p hat should be equal to 0.071 about. And I'll just verify that right here. So what I'm saying is that we're operating under the assumption that this is in fact a fair coin, meaning that 50% of the time it would land on heads, and 50% of the time it would land on tails. we're flipping the coin 50 times, and we get 0.0707, which is about 0.071. And what we're going to do is build a normal model based on that null hypothesis there. So here is a normal model that I already built. I centered it at 50% of the time it lands on heads. And I'm going to make that a little bit smaller here. So, in this picture here, you can see that the mean is 50% of the time it would land on heads. The standard deviation was 0.071, and I counted that many times, 3 times in each direction. And our p hat, I'm going to plot it, 0.32 would be about right here. P hat is 0.32. And since we're exploring the possibility of the proportion of heads is less than 50%, I'm going to actually color in the left side of this p hat here. So we're exploring this possibility. What is the probability of obtaining 16 or fewer heads when flipping the coin 50 times? To do that, we can just find the area under this curve here. And one easy way to do that is to use the normal CDF on our calculator. And I'm going to keep it at negative infinity on the left side and make the upper endpoint, this edge here, 0.32. And our mean of this distribution is 0.5. And the standard deviation is 0.071. So hit enter, and what is the probability of obtaining a result this rare or even rarer? It's only 0.0056. So our p-value is equal to 0.006 if I round it to 3 decimal places. Is there enough evidence to reject the null hypothesis? Well, is our p-value less than 5%? It is. So I would say yes. There is enough evidence to reject the null hypothesis. P is equal to 0.006, which is significantly less than 5%. And to explain further what this p-value means, there is only a 0.1%, if I round this over, there is only a 0.6% chance, of obtaining 16 or fewer heads when flipping a fair coin 50 times. So since there's such a small chance of this 16 or fewer heads occurring under a fair coin, there's enough evidence for us to reject the notion that the coin is fair. So our original assumption, our null hypothesis, was that the proportion of heads that we would expect to see is 50%. That was our null hypothesis. We were operating under the assumption that it's a fair coin. We tested our sample proportion under that model, and we found that it was only this percent, or a 0.6% chance of occurring. And that was enough evidence for us to say that maybe this isn't true then. Maybe the null hypothesis is false because there's such a small likelihood of our sample result occurring under that assumption. Alright, so just to recap. First step, what you want to do is set your null and alternative hypotheses. Then you find your sample proportion and plot it under a probability model that's constructed based on the null hypothesis. You then calculate the p-value, which is the probability of obtaining a sample result of that distance from the mean or further, and then interpret that p-value. If the p-value is less than 5%, that's usually enough evidence for us to say that our null is false. So we usually set the significance level of these hypothesis tests at 5%, but it could theoretically be any significance level. It could be 1% or something else. Alright, let's do another example. I guess you could pause the video, take a moment to read this example. I'm going to upload a Google Classroom assignment with this post. That assignment is not even going to be due until the 8th of May. And this will give you some enough time to really explore these ideas in the next 2 weeks before you even have to submit this assignment. And this problem is very similar to the assignment, so you can kind of go back to this video when you're working on the assignment and match it up with your Google Doc, and kind of just, it really matches up well to this problem here. So, a recent study indicates that women comprise 46% of Europe's workforce. The United States Department of Labor randomly sampled 525 employee records. Out of this sample, 231 employees were women. Is there enough evidence to suggest that there are less women in the United States workforce than in Europe's? What is the null hypothesis in this problem? Well, we want to just first say that the null hypothesis is that the United States workforce is no different than Europe's, that the proportion of women in the U.S. workforce is exactly the same as that of Europe, which is 46%. And our alternative hypothesis, we usually use our sample proportion to kind of determine what our alternative hypothesis is. And it says here, is there enough evidence to suggest that there are less women in the United States workforce? So this is probably going to be a one-sided hypothesis test where we explore the probability of obtaining a sample proportion that's less than 46%. So let's see, 231 over 525 is equal to 44%. So our p hat is 44%, which is smaller than 46%. So our alternative hypothesis is that the proportion of women in the United States workforce is less than that of Europe. We're exploring that possibility. So we still have the same number here and here. Here it says equal and here it says less than. Did we use a one-sided or a two-sided? We used a one-sided. A two-sided hypothesis test would have looked like this. It would have said we're just exploring that the United States is not equal and that it can vary in either direction. But since it says, is there less women in the United States workforce, and we had a sample proportion that had less women, we're just exploring the possibility that perhaps the U.S. workforce contains less than 46%. So this is what we call a one-sided hypothesis test. We used a one-sided test because we're interested in whether or not the U.S. workforce contains less women than that of Europe. So if we were only strictly interested in if the United States workforce contained a different amount of women than Europe's, that would be a two-sided alternative hypothesis. But since we're strictly considering the possibility that the United States has less women, that's why it's a one-sided. The proportion of women in the workforce can be modeled by a normal model. What are the mean and standard deviation of this model? Hint, use the known percentage of women in Europe's workforce as P. So we're going to use this formula here for our standard deviation of P hat, and we're operating under the assumption that the proportion of women in the workforce is 46%. So the mean that we're operating under is that the proportion of women in the workforce is 46%. And the standard deviation of P hat, we're operating under the model that the proportion of women is 46%, or P is 46, or Q is the complement of that, or 54, and our sample size N was 525. What does this equal? Type this in the calculator. 0.46 multiplied by 0.54 over 525. 0.022 if you round it. Okay, so actually, should I round up to 2 decimal places or 3? I'll round up to 3 decimal places. Alright, so now we have to see, is our sample proportion of 44% of women small enough for us to reject the null hypothesis? So we did a sample of 525 women in the United States or 525 employee records, and we found that 231 of those employees were women, which was 44%. So our P hat was 44%. Is that small enough for us to reject the null hypothesis? Well, we're going to build a normal model based on a mean of 46% and a standard deviation of 0.022. So let me get that picture for you. Here we go. So based on this model here, we're going to plot our P hat and see where it lies. 0.44 is about right here, and we were exploring the probability of obtaining less than 46% of women in the workforce, and that means we're going to shade in the left side. So our question is, what is the amount of area that is contained under this curve here? What is the probability of obtaining 44% or fewer of the workforce that are women, if there are in fact 46% of women in the workforce? So we're going to use the normal cumulative density function. Set that left bound at negative infinity. Set our right bound at our sample proportion there is 44%. Our mean was that there are 46% of women in the workforce, and the standard error was 0.022. Alright, so there is a p-value of 0.182 if I round that. The p-value is 0.182. or 18.2%. The benchmark that we usually set as our significance level is 5%. If our p-value is less than 5%, there's enough evidence to reject our null hypothesis. So is 18.2% less than 5%? No. There is not enough evidence. To reject our null hypothesis. While 44% is less than 46%, there is a 18.2% chance of obtaining the sample proportion even if the true proportion of women in the U.S. workforce is equal to that of Europe, 46%. So because there's a pretty decent chance of that occurring, we cannot assume that U.S.'s workforce is any different than Europe's. If there was only a 1% chance of this result occurring, that might be enough evidence to suggest that the United States actually has less women in the workforce. But since our p-value, our alpha, was less than, or was only 18.2%, there's really not enough evidence to say that that is rare enough to reject our null hypothesis. We can't prove that the United States has the same amount of women in it as Europe, but we definitely can't reject that it doesn't. The book makes a good analogy about that if you read it. It compares it to a jury trial in which a defendant is either convicted or released, and when they release them, they say there's not enough evidence to prove the defendant guilty. They don't really declare them innocent, they just say there's not enough evidence to prove them guilty. So that's a very similar idea. Alright, so read the textbook, continue to stay posted on Google Classroom for more videos about this topic. This was only 2 examples, I'm going to post a few more. And reach out to me via email or Google Classroom. I miss you guys. Look forward to hearing from you. Thank you for watching.